chapters 10 through 12, dealing with water and things that dissolve in water and affect our health that are sort of dissolved in water, has to do a lot with something called solubility. So let's take a quick look at that. So our first example, we're going to calculate the solubility of calcium carbonate. So this is a mineral that you would find at the bottom of, say, like limestone lakes, which is commonly in our water samples. Okay, so this is given by an equilibrium constant called KSP. This stands for the solubility product constant. So for calcium carbonate at sort of normal temperatures, this is 8.70 times 10 to the minus 9. So this is something that would be given to you, say, in a table or something like that. Okay, so we want to calculate the solubility, which means how much of this solid ionic compound would we expect to dissolve in some sort of body of water. So we set up an ice table. So what we're looking at is the solid breaking apart into ions. So in an ice table, we deal with initial, change, and equilibrium. So since this is a solid, we do know that some part of this is going to dissolve and reach what's called saturation. So however much of it will sort of be allowed into the matrix of the water will dissolve. So we're kind of going to ignore this. We don't need to know how much we initially have because some part of it will dissolve, but a lot of it is going to stay solid. So initially, we'll say we have none of this. So what we know is that one of these will break apart into one of these. So we're going to lose some amount x of this, and we're going to add some amount x of this, and some amount of x of this. So I have an x here and an x here, because stoichiometrically, one of these produce one of these and one of these. So at equilibrium, we have x of this and x of this. Okay, so what this means then is KSP is going to equal the concentration of calcium 2 plus at equilibrium times the concentration of carbonate at equilibrium, and that equals 8.70 times 10 to the minus 9. Okay, so if we set this up, these concentrations at equilibrium we have put as x, so this equals x squared. Okay, so if we take the square root of both sides, we will get x. So in doing that, we get that x is equal to 9.3 times 10 to the minus 5 moles per liter. Okay, so this is the solubility of calcium carbonate. In regular water, if we put a big sort of chunk or handful of calcium carbonate into some water, we would expect to get equilibrium concentrations of calcium and carbonate at 9.3 times 10 to the minus 5 moles per liter. Okay, so calcium carbonate is one of the things that the solubility is affected by pH. Okay, so solubility affected by pH. And what really is sort of the main culprit there is carbonate. So if you recall, in acidic conditions, like for example, some H pluses plus CO3, 2 minus, will give us H2CO3, which will give us H2O and CO2. Okay, so we do have something like, for example, acid that can react with carbonate. Okay, so what would happen to the solubility of calcium carbonate if we lowered the pH? So let's say we decrease the pH of the water sample. Okay, decrease the pH. Okay, so we're going to look at Le Chatelier to see what would happen here. Okay, so here's our equilibrium that would be affected that we have here in our ice table. So if we decrease the pH of water, this is going to be reacted, or this is going to be used up. So decreasing the pH of water will cause this to react with some hydrogen and essentially remove it. So decreasing the pH means we would remove some of this. Okay, so what Le Chatelier says is that then your equilibrium is going to shift to sort of counter any stress that was added to the system. So our stress is that hydrogen is reacting with carbonate to remove it. So we are going to shift this direction. So we're going to get what I call a product shift. Okay, when you get a product shift, that means you're producing more of the products. So since this is being consumed by the acid, this would shift this direction, so it would dissolve more calcium carbonate to replace those carbonate ions that were reacted down here. So when we do that, we get this product shift. That means we've increased the solubility. Okay, so having acidic conditions for this particular solid would increase the amount of it that dissolved. Again, because the carbonate does react with hydrogen, which again, in an acidic environment would mean there was more of this. So we would shift to replace that, causing more calcium carbonate to dissolve. Okay, so that's kind of a basic solubility problem. Let's get one maybe a little more complicated in here. Okay, so a second one we can look at here. We're going to look at the solubility of cadmium hydroxide. Okay, so cadmium hydroxide this time. So its solubility product constant is 2.0 times 10 to the minus 14. Okay, so this one is a lot larger. All right, so this one a little different. So when we set up our ice table, CdOH2 gives us the cadmium ion and 2 now hydroxides. Okay, so this one we would get 2 hydroxides because we have that 2 right there. Okay, so sorry, this is a solid. Okay, so ice table, same thing if we're going to calculate the solubility. So our ice table, ICE, and same thing, we don't consider the solid, but when this breaks apart to produce ions, we make X amount of this, but since we have this 2 here, oh sorry, this is 0 initially. In our change, we make X amount of this, and we make 2X amount of this. Okay, so we make double the amount of hydroxide. So at equilibrium, we will have double the amount of hydroxide. Okay, so our KSP now equals the 2.0 times 10 to the minus 14, which equals the concentration of cadmium at equilibrium, and it equals the concentration of hydroxide at equilibrium squared. Okay, so because we have that stoichiometric 2 there, we're going to end up squaring this. Okay, so if we put in our values from our ice table, this turns into X, and this turns into 2X squared. So our 2X gets replaced there, so we get 2X squared. Okay, so we get 2.0 times 10 to the minus 14 equals 4X cubed. Okay, so if we divide by 4, and then we take the cube root, we get that the solubility is 1.7 times 10 to the minus 5 moles per liter for cadmium hydroxide. Okay, so in looking at solubility, if you, like in our case here, where we had 2 of the anion, we did have to account for that in our solubility, and remember that does get squared. Okay, so it turns out that hydroxides are very, very sensitive to pH as well. Okay, so there's kind of a twofold way. So hydroxides are similar in the carbonates we just did, where if we increase the amount of hydrogen, so if we did this in acidic, so if we did this, if we had our cadmium hydroxide in acidic conditions, this can react with H+. So OH minus plus H plus gives us H2O. Okay, so in just the same exact way that carbonate reacts with hydrogen to essentially remove it from equilibrium, this does the same thing. So we would expect the same products shift, or we would increase solubility. So again, according to Le Chatelier, if we put our cadmium hydroxide into acidic water, then some of the hydroxide would react with hydrogen to make water, and we would get a product shift or a right shift to replace the hydroxide. So we would increase solubility. Okay, so we would increase solubility. Okay, so hydroxides are sensitive the other direction as well. What happens if we did this in basic conditions? So what if our pH of our water was slightly basic for our cadmium hydroxide? Okay, so for this one, a basic condition means that we have an increased amount of hydroxide ions in solution. So this means right here, we have too many. Okay, so our stress is now we've overloaded this side. We have too much of this for our equilibrium. So the way the system responds, or the way that our reaction here responds, is to shift to remove some of that. So if, again, we're in basic and we have too much hydroxide, it's going to shift in a way to consume some of those, or we're going to have a reactance shift. So in basic conditions, we're going to shift towards the solid, which means we decrease solubility. Okay, so hydroxides are less soluble in basic conditions because there's already some hydroxide in solution. This is called the common ion effect, and I'm going to do an example of that right here next. So you can see that the solubility does in fact decrease if you already have an ion in there. So for example, for this one, we already had, because it's in basic conditions, since we already had hydroxide, we essentially have overloaded this side, which again decreases the solubility and causes a reactance shift there. Okay, so for our last one, we are going to look at the common ion effect. All right, so for this one, we're going to look at lead chloride. So PbCl2, and the KSP for lead chloride, let me see, I wrote that down, is 1.6 times 10 to the minus 5. Okay, so what I want to look at first is the solubility of, let's look at the solubility first. So, okay, so let's look at the solubility in water. Okay, so we have PbCl2 giving us Pb2 plus and 2Cl minus. Okay, so this is our solid. Okay, so we'll go ICE. Initial, since we're just in water, initially there shouldn't be any of that. So we get plus X plus 2X, X, and 2X. So we get 1.6 times 10 to the minus 5 equals X times 2X squared. Okay, so same setup as before because we have one cation, two anions, so get the raised to the first power, raised to the second. So we get 1.6 times 10 to the minus 5 equals 4x cubed again. And now x is equal to 0.0159 moles per liter. Okay, so that's how much lead chloride we would expect to dissolve in 1 liter of water, 0.0159. Okay, so now instead of water, let's say we had a pretty sort of salty solution. So now we want to look at the solubility in a 0.6 molar NaCl solution. So 0.6, that's kind of salty like the ocean. So let's say we tried to now dissolve the lead chloride in ocean water. So PbCl2 Still same process. Okay, but now this time when we go ICE, we initially don't have any lead, but we have some chloride. Okay, so we have this chloride here is a common ion. So because it's 1-to-1, this means initially we have 0.6 molar. And so we have some there. So we initially have 0.6 moles per liter with 0 of this. So still some of this will dissolve. So we still get plus X. And here we still get plus 2X. So we get X. And now we get 0.6 plus 2X for equilibrium. What was initially there and now what we've added to it. Okay, so now we have 1.6 times 10 to the minus 5 equals X times 0.6 plus 2X squared. Okay, so at this point, you might be kind of dreading what might have happened here. A lot of times here, we would start doing like some FOIL, some multiplication to get our quadratic and solve it. But if we take a look, this is quite a bit larger than this. So it's safe to assume, again, because this is thousands of times larger than our KSP, so it's safe to assume that when we solve for X, it's going to be a lot smaller than this. So we're talking like 4 decimal places beyond what we have here. So it's not going to make much of a difference to the magnitude of this number. So for that reason, it's pretty safe to assume that this is small, just like we did with our acids. Okay, so if we do that, we get 1.6 times 10 to the minus 5 equals X times 0.6 squared. We assumed that's small. Okay, so now we can solve. So 1.6 times 10 to the minus 5 divided by 0.6 squared is going to equal our X. So again, just dividing that over. And when we do that, we get 4.4 times 10 to the minus 5 moles per liter. Okay, so instead of having a solubility of up here 0.0159, we have reduced that down to 4.4 times 10 to the minus 5. So essentially what has happened is having that common ion there has reduced the solubility. So again, kind of think about that previous problem, what we did, where when we had something here initially, meaning this started with the overload. Okay, so because we started with something here, because we were in a solution that already had chloride, it caused it to shift this way, which means our solubility will decrease. And that's exactly what we have calculated here. In plain water, we had 1.59 times 10 to the minus 2 moles per liter. Here in that sort of salt water solution, we have 4.4 times 10 to the minus 5. Okay, so kind of a recap here. Calculating solubility requires your solubility product constant, setting up kind of a little ice table here and go ahead and calculating that. Solubility depends really quite heavily on two things. First of which is the common ion effect, which we saw in this problem here. If you already have one of your ions in solution, like we did here with our chloride, it reduces your solubility, and that's all the time. So the common ion will, again, decrease solubility. And from the problem that we did before, these ones here, we found that some ions would be affected by pH. So for example, hydroxides are more soluble in acidic conditions, but less soluble in basic or alkaline conditions. And for carbonates, Carbonates are more soluble in acidic conditions as well, again, due to the fact that hydrogen ions can react with those particular anions, with carbonate and with hydroxide, to shift the reaction towards the product side to produce more ions or to dissolve more of the solid.